Welcome to 12.2, Evaluating Limits Algebraically. This is going to be split up into 2 days, so you can copy as much as you want at one time, but the assignment is kind of split up into two because these are kind of some long notes. So, first things first, finding limits with properties. So if I let b and c be real numbers, and let n be a positive integer, and let f and g be functions with the following limits. So your limit as x approaches c is L. So basically, if I give you one limit, or I give you one function and the limit is L, and I give you another function and the limit is K, if I want to find the limit of x approaches C of b of f of x, so basically a number times a function, you're just doing basically a number times this limit. So in other words, if it was 2 times the function had a limit of 3, then it would be 2 times 3. If I add together or subtract together the two functions, then all you got to do is just add and subtract the two limits. If I multiply two functions together, then all I would do is multiply their limits together. If I divide, I would divide their limits. If I raise it to any power, I would just raise that power to the limits. So if we look at example 1, if we do that with our definition of our limits, hold on, let me change my pen. Okay, so this splitting it up would be the limit as x approaches 3 of x squared plus the limit as x approaches 3 of 2x plus the limit as x approaches 3 of, think of it as negative 4. And so this one, all I would have to do is just plug in 3 in here. 3 squared gives me 9. This one, all I have to do is plug in 3 in here. 2 times 3. Oops. Let's move this up here. 2 times 3 gives me 6. And over here, my limit as x approaches 3 of negative 4 basically is just negative 4 or minus 4. So my 9 plus my 6 is 15, minus 4 gives me 11. Okay, so then the next one, same thing with this one. We're going to split it up into the limit as x approaches negative 2 of 4x cubed plus the limit, oops, that's a 2 minus, as x approaches negative 2 of 1. And yes, you need to write the limit as x approaches every time. If you don't, I'm going to take off for it. Because then you're not talking about limits, you're just talking about functions. So you need to write this every time. And including when you get to calculus, they will make you write it every time, or they'll take off for it when you take an AP test. So then, let's do this again. So this, all I'm going to do is plug in negative 2. So 4 times negative 2 cubed gives me negative 32. This is just 1 over, plug in negative 2, and then this is just minus 5. So I'm going to get negative 31 over negative 7, which means I'm going to get 31 over 7. So you can basically just take it apart and do problem by problem by problem. You're basically just doing substitution. Next one, finding limits with direct substitution. Kind of it basically is what we just did. So instead of splitting it up into more than one, you can basically, as long as this does not need to be factored and nothing needs to be canceled, you can directly substitute in 4 in here and get my limit. 4 minus 5 gives me negative 1. And so then on this one, 2 gets plugged in here. 2 times 2 squared plus 3. So 2 times 4 plus 3, 8 plus 3 will give me 11. So 2 minus 1 for 2 minus 4, I'm going to plug in 2 in here and in here. So that's 1 over negative 2, so that's a negative 1/2. Okay, again, as long as these do not need to be reduced at all, I can plug them in. So if I do 2 over 4 minus 4, that gives me 2 over 0, which is undefined. So my limit, we say, does not exist. That's what the D and E means, does not exist. So if I plug in negative 9 over 3, that gives me negative 3. If I plug in square root of 8 plus 1 over 8 minus 4, That's square root of 9 over 4. Square root of 9 is 3 over 4. So basically, it's just plug and chug and simplify. That shouldn't be difficult. Now we're going to get into things that we love. Trig functions, piecewise functions. So if I plug in pi, and yes, you still need to know your unit circle, tangent at pi, remember pi is over here, this is -1, 0, and your tangents are 0, undefined, back to 0, and so my tangent is 0. Now for piecewise, in section 12.1, we did a graph, and we plugged them in to see if basically your points met. So this would be a does not exist if you had something like this, but if you had an open circle and then a closed one on top of it, then you'd have it at whatever that x value is. If I'm doing it algebraically, all I'm going to do is I'm going to plug in, I want my limit as x approaches 1. So 2 times 1 plus 1. Now be careful, this only applies when this number is the same as this one. If this is a different number than these, then all you got to do is figure out which function it plugs into and plug it in. The only thing you have to be careful of is over here, because when you graph this first one, you're going to graph it to an open circle. You're going to graph this one to a closed circle. So technically, they're both coming towards an x value of 1. It's just whether they look like this or like this. But if this was a 3, then you would just plug the 3 into this function, and that would be the answer. So when this number is the same as these two, I have to plug them into both. That gives me 2 plus 1 gives me 3. If I plug in 4 minus 1 squared, 4 minus 1 is 3. And so since these two are the same, basically from the left and the right, my limit as x approaches 1 is 3. Okay, so looking at this one, this is the same thing. This number is the same as these two. So I'm going to plug in 2 into each one and see if they come out the same numbers. 6 minus 2 is 4. 7 minus 4 is 3. These are not the same. So you're having the scenario where it comes to 2, 4 on the left, 2, 3 on the right. Actually, it's more curved. And they're not meeting, so my limit does not exist. Okay, so next we have to do limits by factoring, because you'll notice if I plug in a 2 right now, I'm going to get 0 in my denominator. But remember, we're not concerned with the points, we're concerned with what's happening as you get to it. So anytime you plug in 2, if this hasn't been factored and you get 0 in a denominator, you're going to have to factor. So this factors to x and x, plus 3 minus 2 over x minus 2. And as long as these cancel, that basically means that you had a hole in that. So you're basically approaching a hole from the left and the right. You're going to plug the 2 into what's left. 2 plus 3 gives me 5. So my limit is 5. So basically you would have a hole in your equation at 2, 5, and from the left and the right, you'd be approaching 5. Okay, next one. Again, if I plug in a 2, I'm going to get a 0, so I need a factor. 5 times x minus 2. Take out an x, x minus 2. My x minus 2's cancel, so I'm left with 5 over x, which means now I can plug in my 2 in here. 5 over 2 is my limit. Okay, next one. If I plug in a 4, again, I'm going to get 0. I'm going to get 0 over 0. So x minus 4, you're going to have to basically go back and remember all of your factoring, all of your trig, all of your piecewise functions, anything. Heck, I could even put a log in here if I wanted to. Cross off the x minus 4s. That leaves me with 1 over x plus 4. And so now this 4 can be substituted in here. 1 over 4 plus 4 gives me 1/8. Okay, number 15. The limit as x approaches 5 of x squared minus 6x plus 5 over x squared minus x. So the top is going to factor to x minus 5, x minus 1. The bottom factors to x minus 5, x plus 4. So my x minus 5's cancel. And I'm going to plug in 5 in here and in here. So 5 minus 1 over 5 plus 4 gives me 4 over 9. Okay, next one, I'm going to factor, I've got limit as x approaches 0 of 3x cubed minus 6x squared over x squared minus 2x. We're going to factor a 3x squared out of the top, and I have x minus 2 left over. And on the bottom, I'm going to factor out an x minus 2. So my x minus 2's cancel. Then I'm going to plug in 0 in here. Oops, I forgot to do another one. Let me erase that. Spoke too soon. We also can factor, or we can cancel out one of the x's. So I'm left with 3x. And now I can plug in a 0 in here. 3 times 0 gives you 0. Okay. So now this one, you could try to factor this by grouping, or I'm going to just do synthetic division, because I know if this is x plus 2, I know it's probably going to factor, because if I plug in a negative 2, I'm going to get 0. So I'm going to assume that x plus 2 is one of the factors up here. So if this is x plus 2, I'm going to use minus 2 for my synthetic division, and it will make it easier to factor it down. So that is a 1, a negative 3, a negative 4, a 12. So 1, negative 2, negative 5, 10, 6, negative 12, 0. So I'm left with x squared minus 5x plus 6. So this factors to x plus 2. And then x squared minus 5x minus plus 6 is x minus 3, x minus 2 over x plus 2. So my x plus 2's cancel. And then I'm left with plugging in negative 2 in here and here. So negative 2 minus 3, negative 2 minus 2 is negative 5 times negative 4, which gives me positive 20. Okay, so ignore this little thing. I don't know how that extra thing got up there. Sometimes when you want to find limits, you have to rationalize. And this time, you already know how to rationalize denominators. We're going to rationalize numerators. Because right now, if I plug in a 0 here and a 0 here, I'm going to get 0 over 0. So there has to be a way for me to do it, so I'm going to rationalize the numerator. So in this case, you're going to rationalize the numerator, which means if I have square root of x plus 1 minus 1 over x, I need to multiply by its conjugate, square root of x plus 1 over square root of x plus 1 plus 1. When I FOIL, okay, that's going to give me x, square root of x plus 1 times square root of x plus 1 gives me x plus 1. Then my outside and my inside will cancel. And then when I do my last, my negative 1 times my positive 1 is negative 1. However, when I multiply the bottom, let me do this in purple, I'm not going to distribute. I'm just going to leave it as x times square root of x plus 1 plus 1. And I'll tell you why in a second. So these cancel, and I'm left with x over x square root x plus 1 plus 1. And if you do it neatly, this is what should happen, is these will cancel. If I FOILed it back here and left it x times square root of x plus 1, x times x plus 1, or x times 1, you wouldn't have seen that these cancel. So I'm left with 1 over square root of x plus 1 plus 1, which means when I substitute in 0, let's do it here. I get 1 over square root of 0 plus 1 plus 1, which is 1 over square root of 1 plus 1. Square root of 1 is 1. 1 plus 1 is 2. So it's a half. Okay, same thing over here. I'm going to multiply by the conjugate. So I'm going to multiply by 3 plus square root of x. 3 plus square root of x, which gives me 9. And I'll just multiply it all out. Plus 3 root x minus 3 root x minus x over, and again, I'm going to leave my denominator like this instead of foiling out the denominator. So try not to foil the denominator. because it will be easier for you to factor things out. These cancel, and I'm left with 9 minus x over x minus 9, 3 plus square root of x. Now these two are almost the same. In order to cancel these out, I'm going to have to factor out a negative 1. So I'm going to factor a negative 1 out of the top. So that gives me negative 9 plus x over x minus 9, 3 plus square root of x. Then these cancel, and I'm left with let me make another color. Negative 1 over 3 plus square root of x. And now I can substitute in 9 here. So it's negative 1 over 3 plus square root of 9. Negative 1 over 3 plus 3 is negative 1/6. Okay, so finding limits of a polynomial at infinity. Okay, so let's think back to your end behavior. Okay, so when n was even, your graph on the ends either went both up or both down. And when they were odd, they went in opposite direction. One up, one down. Okay, those were the ends. And then you had all your stuff in the middle, depending on what your graph looked like, all that stuff in the middle. So you can kind of think of limits as the same thing. As my limit as x approaches negative infinity, meaning going on the left, if they're both going up, then it's going towards positive infinity. Same thing if my limit goes towards positive infinity. Okay, so if we look at limits of rational functions, so a rational function is just one that is a fraction. So if I type in, and right now I'm just showing you these, you can certainly look in your calculator and see what it looks like. But if I type in x squared minus 2 over, I'm doing this on the calculator as I'm just talking this, x squared plus 2, you're going to get a graph that looks something like this. Okay, so it ends up looking something like this. Okay, so my limit as I'm approaching, and it looks like it's at about 1. My limit as I'm approaching negative infinity is getting closer to 1. My limit as I'm getting closer to positive infinity is 1. So on both sides, that's 1. And you might notice that is the same as your horizontal asymptote. Same as where your horizontal asymptote is. Okay, so if I plug in 4x plus 3 over 2x, your graph is going to look like this. You have an asymptote here. You have one here. Your graph looks like this. Okay, so as my equation gets closer to negative infinity, you're getting closer to 2. And when I'm going towards positive infinity, I'm getting closer to 2. So again, 4 over 2 is the same as your horizontal asymptote. Okay, so when we look at these ones, when I look at y equals 2x plus 1 over x squared minus 1, and I graph it, my graph looks like this. You have a vertical at 1, you have a vertical at negative 1, and you have a horizontal at 0. And my graph actually looks like this. It crosses over the center. You have one up here. But we're not concerned with all of this stuff in here. I'm concerned with on these ones going to infinity. So as I'm going to infinity over here, it's going to approach 0. As I go to positive infinity, it's approaching 0. Next one, if I do x squared plus 2x plus 1, oops, I gotta put in the 2, over x minus 1 and graph it, you get this graph. You're going to get a slant asymptote. Hold on, let me see where the slant asymptote is. So x plus 3. So 1, 2, 3. So you're going to have a slant asymptote at y equals x plus 3. You're going to have a vertical or a horizontal one. No, not a horizontal one, sorry. A vertical one at 1. My graph ends up looking like this and up here. And so as on these ones, as we look at your asymptote, hold on, I need to change colors. On the right, this is going towards positive infinity, and on the left, it's going towards negative infinity. Okay, so really your limit doesn't exist. Okay, so if you keep in mind like how you did a horizontal asymptote, so my horizontal asymptote you would get by taking your largest variable, which is x squared, and its coefficient on top is 0, and its coefficient on bottom, oops, sorry, not 0. 1. It's not going to let me write. So my coefficient for x squared on top is 1. Coefficient for x squared on bottom is 0. So my limit doesn't exist. So I don't care whether you graph it out or whether you just tell me they both don't exist. Because technically they don't, because a limit is where you're getting closer and closer to a number. But infinity, technically, you're never actually going to hit. Okay, so on all of those ones, for any integer that is limits x approaches infinity of 1 over any variable, it doesn't matter whether there's more x's on top than bottom, whatever you get, or when there's more x's on bottom, you get 0, and anything to the 0 power, you get 0. So to find the limit of any function, divide each term in the equation by the variable with the largest exponent, then simplify. You'll notice that when you find your limit to infinity, the limit is approaching the horizontal asymptote. So mathematically, what they're going to have you do, I'm going to do this the long way because you're going to have to do this in calculus for a little while. They're basically saying, okay, my largest variable is x cubed. So I'm going to divide everything by x cubed. Squared divided by x cubed minus 2x over x cubed over 3x cubed over x cubed. So you're dividing each one by x cubed. Oops, wait, that's squared. And you're looking at its limit. All right, let me make this smaller. Okay. So your 4 over x cubed basically just gives you 4 plus, this is 3 over x. This is minus 2 over x squared. And then this is 3 minus 2 over x plus 7 over x cubed. And so before we said that anything that basically is 1 over x to the anything power, its limit basically is 0 for this one, 0 for this, 0 for this, 0 for this. So that's why that little trick that I taught you at the beginning of the year works, because your limit is 4/3. It's just the largest variable, the coefficients of the largest variable, and then take those coefficients on top and bottom. So when I do the same thing over here, my largest variable is x squared. So everything else basically is not going to matter. So all I'm going to do is take the 4 over the 3. When it's your limits to infinity. If it was to a number, you need to plug it in. Okay, so when I look at this one, my largest variable is x squared. So my coefficient for x squared on top is 1. There is no x squared on bottom. And all of these won't matter because they'll all be zeros. So basically 1 over 0 does not exist. Your limit does not exist. Or if you actually graph it, it's going to give you infinity. So here again, my largest variable is x squared. So all of these are not going to matter. So my coefficient for x squared on top is 0. My coefficient for x squared on, for x squared on top is 0. Coefficient for x squared on bottom is 1. So 0 divided by 1 is 0. Okay. Again, here, my x is my largest variable, so these are not going to matter. So it's going to end up being 2/3. Over here, my largest variable is x squared. Anything smaller is not going to matter. So my coefficient for x squared on top is 2. There's no coefficient for x squared on bottom. So it's 0, so it does not exist. Or if you want to graph it, oh, that's a bad E. If you want to graph it, then you can see better whether it's going to be infinity or negative infinity. And AP actually takes both of them. So finding limits of rational functions of sequences. So we did sequences already, and we kind of talked about them. Your limits of sequence have many of the same property as the limits of functions. So for example, if I have 1/2, 1/4, 1/8, 1/16, they're getting smaller and smaller and smaller and smaller. I want to know, what is the sequence getting closer to? It's getting closer to 0. So if the sequence gets closer to a particular number, we say it converges. We kind of talked about that last unit. If the sequence does not converge, meaning they get bigger and bigger and bigger, it diverges. So, for example, if I have -1, +1, -2, +2, -3, +3, if I keep going with that pattern, it's going to get bigger and bigger, even though it's going both ways. That's still considered divergent. Or if I have 1, 2, 3, 4, 5, 6, they're getting bigger and bigger, and they're not going to merge towards a certain number. That's a divergent sequence. Okay, so in example 33, a sub n equals n over n squared plus 1. I want to write the first 5 terms. So if I plug in 1, I'm going to get 1/2. If I plug in 2, 2/5, 3, 3/10, 4, 4/17, 5, 5/26. So if you notice, these numbers are getting closer and closer and closer and closer to 0. So it converges, and its limit is 0. Okay, and so you'll notice, if you look here, kind of like we did when we did the rational functions in the last one, this is kind of a rational sequence. So you can do the same thing. My largest variable is n squared, so I really don't need these. So my coefficient for n squared on top is 0. Coefficient for n squared on bottom is 1. 0 divided by 1 is 0. So it matches whether or not you look at the rational part of it or whether you look at the sequence of numbers. If I look at example 34, okay, my first 5 terms, if I plug in a 1, I'm going to get -4. If I plug in a 2, I'm going to get -2, 3, 0, 4, 2, 5, 4. Okay, and its numbers are getting bigger and bigger and bigger and bigger, so it diverges. And so my limit doesn't exist. You can also see that here. If I make this a fraction, my largest variable is n, so technically this is 2n minus 6 over 1. And so these are not going to matter. So my coefficients are 2 over 0 for the coefficients for n, which means my limit doesn't exist. So they're the same. Okay. Example 35, a sub n equals 4n squared plus 1 over 2n. Write the first 5 terms. So if I plug in n, my first 5 terms are going to be 5/2, 17/4, 37/6, 65/8, 101/10. Okay, so those are getting bigger and bigger and bigger, even though they don't look like it. This is 2.5. This is a little bit more than 4. This is a little bit more than 6. They're getting bigger and bigger. It diverges. So if it diverges, your limit doesn't exist. So if I look again over here at my rational function, n squared is my largest, so these are not going to matter. So I'm basically doing 4 over no coefficient for n squared on bottom. So 4 over 0 does not exist. Okay, so n factorial over n gives me 1, 2, 6, 24. Hold on. 5 factorial, 5. Oh, well, let me try those again. So 1 factorial, hold on, n factorial divided by n. I missed writing down a number, so I have to do it again. Okay, so if I plug in a 1, oh, because there's 2 1s. Sorry, that's why I forgot to write down. So it's 1, 1, 2, 6, 24. Okay, these are getting bigger and bigger and bigger. It diverges. And so it doesn't exist. Okay, this one is going to be a little bit harder to do. You can't necessarily do it because your largest variable is going to be it's not going to be the easiest thing to tell on this one, so I would just write those out for this sequence. Okay, so here is a hard one. I want to know what the limits of the sequence is and not to use a calculator. So really remember, with this whole thing is a rational function, so I really just need to figure out what my largest variable is going to be. So really my largest variable is going to be from the 9, the 2n squared. This, when I FOIL it out, is going to give me another 2n squared. And this, when I FOIL it out, will give me another 2n squared. So I really don't care about anything else, but I have a 9, I have a 2n squared, plus this will be a 2n squared times 2n squared when you multiply it out, which means these two are going to make a 4n to the 4th when you multiply them out. So really, this is not going to matter either, because that's going to be the larger one. So when I do 9 times 4, I get 36n to the 4th over 24n to the 4th. And since these are the same, it's just 36 over 24, which if you divide by 4, you get 9 over 6. If you divide by 3, you get 3 over 2. So it's not really as hard as it looks. You kind of have to pretend you're multiplying the whole thing out and figure out what you have.